Hi everyone, welcome to this session. So in this session, I'm gonna cover what are the common interview questions that people ask in quantitative finance, and this is specific to linear regression. So I've seen like linear regression as one such topic that is favorite for many interviewers, and they because they also understand linear regression quite well, and it is commonly used also by the industry. So let's see what are some of the interview questions and how to answer them. So, the first question is, okay, what is linear regression and can you explain the types? And, this is just to make you understand. I mean, the interviewer asks you this question so that you understand, okay, what is it and what are different types of it. So, to answer it, what we can say is linear regression, and I'll refer linear regression with LR, okay? So, linear regression is a statistical method which is used to analyze the relationship between a dependent variable and one or more independent variable. So it's a statistical method which is used to analyze the relationship between dependent variable and one or more independent variable, right? So so in other words, we can basically say that linear regression is used to predict the value of dependent variable. So linear regression is used to predict the value of dependent variable based on the values of independent variable. And how does it work, right? How does it work? How does it work is basically linear regression tries to find the best fit, or let's say tries to find the best line that fits the data. Okay. And it is also known as the line of best fit. So you might be thinking, what is the line of best fit, right? So the line of best fit is nothing but a straight line which minimizes the difference between actual data and predicted data. So this is how to describe linear regression, right? It's a statistical method which is used to analyze the relationship between dependent and independent variable. It can be used to predict the values of, or let's say it is used to predict the value of dependent variable based on different values of independent variable. And how it does it does by trying to find the best fit line which minimize the difference between actual and the predicted data. So now to answer what are the different types of linear regression, right? So there are two types of linear regression, that is a simple linear regression and a multiple linear regression. Let's understand what is simple and what is multiple. So in simple linear regression, you'll have just one independent variable. And then and in multiple linear regression, you'll have more than one independent variable, right? So to write it in mathematical terms, simple linear regression can be written as y is equal to b naught plus b1 x1. Okay. So in this case, your y is nothing but your dependent variable. And why is it called dependent variable? Because it depends on the value of x1, right? If you see this equation, right, the value of y depends on the value of x1. So that's why y is the dependent variable and x1 here is independent variable. So this is the mathematical form of simple regression. Now B naught, and what is B naught and B1, right? B naught is nothing but your intercept, and B1 is nothing but your coefficient of x1. Okay. So this is how your simple linear regression looks like. Now second is multiple linear regression. And how to define it is by this. Y is equal to B naught plus B1 x1 plus B2 x2, right? Plus, and it can go up till Bn xn. So once you have more than one independent variable, then that categorizes into multiple linear regression. Okay. So here again, y is nothing but your dependent variable, right? X1, x2 up till xn is nothing but your independent variable, and b1, b2 up till bn is nothing but your coefficients of x1, x2 up till xn. Okay, I hope that is clear, right? So the next question, and this is like the most important question, most important. What are the assumptions of linear regression? Right. So always keep this word in your mind. Okay. LAH, LAHMN. So this is how I used to remember in my interviews. If you have heard about Lehman Brothers, right? Right. So how I remembered was by the term layman. Okay. So now let's see what is layman. L. So here L, which is like the first assumption. So the first assumption is nothing but linearity. Linearity means that the relationship between dependent and independent variable should be linear. See if if the relationship is linear, right? That's how you will use a linear regression. If the relationship is not linear, then you will use a non-linear regression model, right? So the first assumption is that the relationship between the dependent and the independent variable should be linear. Second assumption, A. So A stands for autocorrelation. Okay. So this assumption basically says that there should be no autocorrelation between the residuals. So there should be no autocorrelation between the residuals. So which basically mean that um, so this basically mean that your current value of residual should not be dependent on previous values of residuals. And in this case, residual is what? What do you mean by residual? It's nothing but your actual value. Okay, your actual value minus predicted value. And this is what we say as residual. See, when you use a linear regression model, right, you'll have the actual value of y, right? And using the model, you'll predict. So this is, let's say, y actual, and you'll using the model, you'll predict the value of y, right? Using the linear regression model. So the difference between your actual value and your predicted value is what we say as residual. So what I'm saying here is the current value of residual, right? So let's say we have certain observations, right? We have certain values of y here, right? So sorry, let's say we have certain values of residuals here. So what I'm saying is this value should not impact the next value, should not impact the next value, this value should not impact this value, right? So so if you think what will happen if this gets impacted? So the main thing is, see, if we have residuals, what so residual is nothing but your error in your model, right? Your error in your model. So if these are related, so this error will impact this error, which will impact this error, which will impact this error. So over time, right? Over time, what will happen is, if let's say this was your actual and this was your, let's say, predicted, right? Let's say, so this will be the case when there is no autocorrelation, right? But let's say if there's autocorrelation in your residual, right? What will happen is, let's say this is your actual, so this will be your predicted. So the error term will increase, increase, and increase because this error will also impact this error, will also impact this error. That's why when we are modeling, we do not need any autocorrelation between the residuals. So this is the second point. Third point, H. H stands for heteroscedasticity. So basically, what does this mean? So this basically means that the variance of the residual should be constant across all level of independent variables. Okay. So what does this mean? The variance of the residual should be constant across all the values of independent variable. See, if let's say there is heteroscedasticity present in your linear regression model, it will, if let's say heteroscedasticity is there, right, it will impact your standard errors. And if your standard errors will get impacted, the model will throw incorrect results. So, and we do not want this thing to happen, right? And that's why we say there should be no heteroscedasticity, or let's say we basically say that the variance of the residual should be constant across all the independent variables. So that's why there should be no heteroscedasticity. Also, sorry, this definition what I just wrote is of homoscedasticity. Sorry. Okay. So this is nothing but homoscedasticity. Okay, so that's why we say there should be no heteroscedasticity present. Because if the heteroscedasticity will be present, then the variance will not remain constant. And if the variance will not remain constant, there will be, this will impact the standard error. And if that impacts the standard error, then the model will throw incorrect results. So that's why we say there should be homoscedasticity present in the residuals, and there should be no heteroscedasticity present in the variables, in the residuals. Fourth assumption, normality. Okay, or let's say normality. So this basically says that the residual should be normally distributed, right? And your fifth assumption is nothing but multicollinearity, which stands, so this stands for N, this stands for M, multicollinearity, which basically means that, so we say that there should be no multicollinearity present in the model, present in the model. This means that This means that the independent variable, right? Which in our case are what? X1, X2, up to Xn, right? The independent variable should not be highly correlated with each other. So these are the 5 assumptions of linear regression. I'll walk you through again. First is, okay, just remember this term layman. So L stands for linearity, that there should be a linear relationship between your dependent and independent variable. Then A stands for autocorrelation, that there should be no autocorrelation present between the residuals. Okay. The third term is H. H is homoscedasticity, that is the variance of the residual should remain constant across all the values of independent variables. Fourth term is M stands for multicollinearity, that there should be no multicollinearity present in your there should be no multicollinearity present in your model. That is, the independent variable should not be highly correlated. And the last term is N, which is normality, which is the residual should be normally distributed. Just remember this term and this will make your life easy. Now, see, these are, basic questions, right? Now, interviewer further goes into deep. So what all questions he can ask you is how to measure, right? How to measure linearity between your dependent and independent variable, right? So, to do this, right? See, the thing is, if you see this assumption, right? This which is layman, right? Always remember this term, layman, right? So the interview will ask you each and everything regarding to each of the assumptions, okay, how to measure linearity or how to measure autocorrelation, how to measure heteroscedasticity, how to measure multicollinearity, how to measure normality. So let's focus on that, how to measure each and everything. And that's how you can say, no, I mean, okay, the assumptions are met or the assumptions are not met, right? So the first thing, how to measure linearity between dependent and independent variable. So the first thing or the first way can be by using correlation. Okay. So basically what we are going to say is to measure the linearity between a dependent and independent variable, one common matrix is correlation coefficient. Okay. So correlation coefficient is nothing but it measures correlation coefficient measures the strength and the direction of the linear relationship between two variables. See, if you have heard the term Pearson correlation, right? If you have heard the term Pearson correlation and this correlation are just the same. Pearson correlation and correlation. So when someone say okay the correlation, they actually refer to Pearson correlation. Pearson correlation. So and remember this thing, Pearson correlation is a measure of linear relationship. So if let's say if there's a non-linear relationship, then Pearson correlation won't be able to measure that. Okay, and this is for your modeling knowledge. Okay, so if so basically Pearson correlation is used to measure the linear relationship. Okay, so how can it does so what it does is it basically measures the strength and the direction of your linear relationship. Okay, so let's understand it in greater detail. Let's say this correlation can be denoted by rho. Okay, so let's say now this rho, okay, this is this for your knowledge, rho can take the value between -1 to 1. Okay, so here -1. Okay, -1 represents a perfect negative linear relationship. Okay, So what it means is when let's say rho is equal to -1, it means that let's say our equation is something like this, okay? Something like this. So let's say if x1 increases by 1 unit, y will decrease. If x increases by 1 unit, y will decrease by 1 unit. And this is what rho is equal to -1 means, okay? Then rho is 0, right? It basically means that there is no linear relationship, no linear relationship. And then rho is equal to +1 means perfect, perfect, positive, linear relationship. Okay. So using the concept of Pearson correlation or just the correlation, both the same, you can measure the strength and the direction, right? So in this, right, when I say, okay, rho is equal to positive 0.75, right? So plus is nothing but your direction, and this is nothing but your strength, okay? So this is one way of analyzing if there exists a linear relationship or not. There is one more way, okay? There is second way, which is by using scatter plot. So what you can do is basically, you can basically do a visual inspection, or you can plot a scatter plot, visual inspection, or let's say you can plot a or you can plot a scatter plot between your dependent and independent variable. Okay. And if let's say this is your dependent and some, okay, let's say this is your dependent and independent variable, right? And if your scatter plot is something like this, right? Let's say something like this, right? So if let's say if it's roughly linear, if it's roughly linear, right? Then we can pretty much say that it follows linear relationship. Okay. Okay. So these are two ways in which you can understand. So one is using the correlation coefficient, and the second is using the scatter plot to understand if there is a linear relationship between your dependent and independent variable. Now your fourth question. So this was okay. Fourth question is, what if autocorrelation assumption is not met? Is not met in the linear regression model. So if let's say if the or okay, so let's say if there is autocorrelation between the residual. Okay, assuming let's say if if there is autocorrelation between the residual, what it actually means is that the model is not fully capturing all the relevant information in the data. Okay, model is not fully capturing all the important, or let's say all the information, all the relevant information in the data, and there is still some underlying pattern. Okay, there is still some underlying pattern in the residual that needs to be explained, right? So now this is what will happen if there's a autocorrelation between the residual, right? That why it happens is because model is not able to fully capture the relevant information from the data set we have, and there's some underlying pattern which we have not captured using the model. So, so what will happen? Now let's say what will happen. Let me answer this, right? So if autocorrelation is not met, if autocorrelation is not met, right, it will lead to inefficient estimates. It will lead to inefficient estimates of the regression coefficient. And see, if regression coefficients are not estimated properly, right, this will for sure impact the reliability of our model, right? So it will affect the reliability of the it will of the statistical inferences from the model. Let's say from the statistical inferences made from the model, right? I hope you understand, right? So if let's say if they if or by this part basically tells what will happen if we see autocorrelation between the residuals, then of course the will not get the will not get the proper estimates of a regression coefficient, and that will definitely impact our model. Okay, so you might be thinking, how will we understand, Mehul? Like, how will we understand, right? If there exists autocorrelation or not? Okay, how to check for autocorrelation, right? How to check for autocorrelation? You might be thinking, right? So the way to check for autocorrelation is by using statistical tests such as Durbin Watson test. It is also called the DW test. Okay, Durbin Watson test, or it can also called the DW test. And this test is actually used by practitioners or the industry people to formally test for the presence of autocorrelation, to test for the presence of autocorrelation between the residuals. Okay, so now let's understand this test. Okay, what is Durbin Watson test? Okay, let's understand this test, because these are some questions, which see, it depends a lot on what's the background of the interviewer. Sometimes the interviewer will go deep, and sometimes he'll just cover the basic questions. Okay, what is assumptions of linear regression, and okay, what are the types, and that's it. But in some cases they'll go in actual deep. So let's understand this Durbin Watson test. Okay, so basically it's a statistical test. It's a statistical test, as I said, used for analyzing or used for detecting autocorrelation in the residual of a linear regression model, right? So now we have, as we all know, in a statistical test, we'll have a null hypothesis and we have an alternate hypothesis. So the null hypothesis in this case is there is no autocorrelation between the residuals, right? And your alternate hypothesis will be there is autocorrelation. See, when you perform this DW test, right? It gives you a range. It gives you a range. Okay. So basically, it gives you a range between, I guess, 0 to 4. Yeah. This test gives you a range between 0 to 4, and it has different implications to it. So let's say if your DW test, right, gives you a range between 0 to 2 to or 2, or it will give something between 2 to 4. There are only three cases. Okay. So if it gives you a range between 0 to 2, it basically means that you have a positive autocorrelation in your residual. Okay, a range of 2 basically means there is no autocorrelation. No autocorrelation. Okay, and a range of 2 to 4 means there is a negative autocorrelation. So you might be thinking, Mehul, I mean, it's good. I mean, we understood how to analyze. I mean, the Durbin-Watson test will perform this test, will get a range, and we understood, okay, whether if there's any autocorrelation between the residuals or not. Okay, if it's good if it's not there, but what if it's there, right? You might be thinking. So that's where the use of all these time series models, right, came into existence, right? Because if you see auto-regressive model, moving average model, ARIMA model, right? If you see one of the assumptions of this time series models were the autocorrelation remains constant. Autocorrelation between the residuals remains constant. So even though it's constant, but it's still capturing the autocorrelation, right? And in linear regression, what we are saying is there should be no autocorrelation. But in all the time series model, autocorrelation is allowed, but the only thing is it should be constant. So this is one way in which you can improve your model by including any time series modeling, or you can do all the differencing. So when you do the differencing, it is seen that the autocorrelation sometimes goes away. So doing differencing will help you to remove the autocorrelation. So this is how you measure the autocorrelation between the residual by using the DW test. So again, linearity can be measured by using Pearson correlation or a scatter plot. Then we have autocorrelation, which can be measured by using the Durbin-Watson test. And see, always remember when you are interviewing, right? I mean, the interviewer can ask you, okay, how can you check for autocorrelation between the residuals? Then just say, okay, so DW test is a very famous test which is used by practitioners to check if there's any autocorrelation which lies between the residual or not. The null hypothesis of the test says that there is no autocorrelation between the residuals, while the alternate hypothesis says that there is a autocorrelation between the residual. So when we perform this test, it actually gives a range of number between 0 to 4, indicating if we get a Durbin-Watson test between 0 to 2, it says positive autocorrelation. A number of 2 basically means no autocorrelation, and a number between 2 to 4 basically says a negative autocorrelation. Also, this can be basically removed by including a time series model or by performing differencing. So this is how you need to answer in your interviews. Question 6. Again, so we have covered L, we have covered A, how to measure linearity, how to measure autocorrelation. Now H, how to measure that's how to measure homoscedasticity, right? In the linear regression model. Okay. So as you remember, homoscedasticity is what, right? Is if we basically, it's nothing but your error term, right? Should remain constant across the values of independent variables, right? So how can we check it, or how can we measure it? So what we can do is we can basically measure it by plotting a scatter plot. Okay. So we can measure homoscedasticity by plotting a scatter plot. Okay. By using this, you can measure homoscedasticity. So what happens is when you plot residuals with independent variables, okay. So generally, if it gives you a cone-like structure, sorry, if it gives you a cylinder like structure, let's say your residuals are in this format, cylindrical format, right? So this means that your residuals are homoscedastic, that the variance is constant, right? If you see, this variance is constant across different values of the independent variable, right? So when we say homoscedasticity, basically means there is no heteroscedasticity. Okay. But when you do a scatter plot, okay, let's say between your residual and your independent variable, and if you get a cone-like structure, let's say if you get something like this, and if your residuals are something like this, so if you say it's distributed all over the place, right? It is not constant anymore. So this is where we say that there is a presence of there is a presence of heteroscedasticity in the linear regression model. Okay. So I hope you understand this, right? I mean, how can we measure heteroscedasticity? Is by basically plotting a scatter plot. So if you get a cylindrical like structure, then you can say that your error term is constant. But if you get a cone like structure, right, then you can say that your error term is not constant, and that's what implies that there is a heteroscedasticity present in your linear regression model, right? So, see, of course, right, when you have heteroscedasticity, you need to look out for solutions, right? You need to look out for solutions. So, so basically, what you can do is there are some transformation techniques which you can use, right? So the solution is there can be some transformation techniques which you can use. Now you might be thinking, like what kind of transformation, right? So transforming basically so transformation technique can be basically applying, let's say, logarithm, or let's say applying square root, or some other transformation you can do on your dependent variable, and this will help you remove your heteroscedasticity. Okay. Another approach can be applying weighted least square regression technique. Okay, this is weighted least square regression technique. So what is weighted least square regression technique? Weighted least square basically means that so weighted least square regression techniques, what it does is it assigns different weights to the observation. Okay, and this weights will be based on based on the variance of the residual. So basically you will apply higher weight to smaller residuals, right? And less weights, and then less weights to higher residuals. So this is how you can basically, understand, okay, if there's a presence of heteroscedasticity in the model by plotting a scatter plot. And then if you see, okay, if you see there is, then you can basically transform your dependent variable by either taking a logarithm, square root transformation, cube root transformation. There are different kind of transformation techniques, right? And then, or you can apply a weighted least square regression model in which you need so if you see linear regression models, right, if you see a linear regression model, it assigns equal weight to all the observation, right? Equal weight to all the observation, right? So in this least square regression model, you assign different weights. So higher weight you'll assign to smaller residuals. Again, residuals is nothing but the difference between actual and predicted value, right? And you apply lesser weight to your higher residuals. So I hope this is clear. So we have covered LAH. Now is M and N. Okay, so let's cover multicollinearity. So this is question 7. How to detect multicollinearity in a linear regression model, right? So this is like really okay. Before going deep into the test, what is multicollinearity, right? What is multicollinearity? Multicollinearity is nothing but it refers to a higher correlation between two or more independent variable in the model. Okay, high correlation between two or more independent variable, and this is like very common, So I'll give you a live example. I was working on a credit risk data set. There were two variables, FICO high, FICO low. FICO is nothing but your credit score. Okay. And the values were exactly the same, 585, 700, 780, 640. The values were exactly the same. So in this case, when the correlation is high, in this case, your correlation will be 1 because it's exactly the same, right? So you need to drop one variable. So if let's say these two variables are there in your data, right, and you are running a linear regression model, so it will have a higher collinearity because you have you have two independent variables which have a higher correlation. In this case, a correlation of 1, which is like the maximum value it can take, right? So that's why in this we can say that we can say in this that there is a presence of multicollinearity. There is a presence of multicollinearity. Excuse my handwriting. So there's a presence of multicollinearity, right? But see, this is just I've taken, for observation. But when you are dealing with, big data set, let's say you have 200,000 customers, 300,000 customers, it is not wise to, check each and every observation, right? So that's why basically, these researchers or statisticians, they made a test which is called the variance inflation factor, VIF, right? VIF in short. So what this VIF indicates is if there are any correlated variable present in your data set or not. Okay. So this if you see this VIF factor, it helps you to understand the correlation. Okay. So it basically has a value from 1 to infinity. Okay, the VIF takes the value from 1 to infinity. So basically how we say is, okay, if the VIF value is less than 5, so it basically means that there is no multicollinearity. Okay, if VIF is between if VIF is between 5 to 10, okay, so it basically means moderate level of multicollinearity. Moderate level of multicollinearity. And if it's greater than 10, then this means high level of multicollinearity. So we have a danger in this case. So if you see that when you perform this VIF, and if you see that your variables have VIF greater than 10, then you need to drop. So what will you do? You will need to drop one variable, because if you drop both the variables, it doesn't make sense, right? If these both are telling the same thing, I mean, you can drop either one this or either this, right? Just drop one variable and that's it, right? So this is what we say for multicollinearity, right? And the last is how to detect normality, right? Are you able to understand this, or am I too fast? Please let me know if in case you have any doubts or you are not able to understand anything. So how to detect normality in the regression model, in the linear regression model, right? See, normality is the most important assumption of the linear regression, okay? Because it ensures that the error term, right, are distributed randomly and there is no bias in any particular direction, okay? So, so just this is just for you that normality of residuals is an important assumption, of linear regression model because it makes sure or it ensures that errors are distributed normally and are not biased in any direction. See, if you see a normal distribution, it is like this, right? Something like this, right? So, so when errors are distributed like this, it's still good. But let's say if it's skewed, so something like this or something like this, then this is a issue. You need to solve this. These both are issue. When you plot your diagram and if you see residuals in this shape, it is not in. So this is what is ideal. But if you get this or this shape, then you need to work on your normality. You need to work on this assumption. But the question is, how will you detect, right? What's the way to detect it, right? So method to detect it is first is by plotting a histogram of residuals. You can basically plot a histogram of your residual. So what is this, right? See, if you see histogram is nothing but this, right? So when you plot a histogram of your residual, right? So it should come something like this, right? So this is, if you see, this is nothing but, if you see, you can draw a normal distribution like this, right? Oops, something like this, right? So if you're when you plot your histogram and if it's in the shape of normal distribution, then you can say that the assumption is met. Okay, assumption is met, right? So this is the first way of understanding if like how to detect the normality of your residual. Okay, the second way is QQ plot. The second way is QQ plot. QQ plot. So QQ plot is nothing but your quantile plot. Okay, QQ plot is nothing but your quantile plot. So what it does is it is basically it can be used to compare. It can be used to compare the distribution of the residual, to a normal distribution. So it actually compares. Okay. Okay. So if if let's say the residuals are normally distributed, right? If the residuals are normally distributed. So it basically means that the data point, see, the data point should follow a straight line. The data point should follow a straight line. Okay. See, if you see a QQ plot now, it will be something like this. So your data will be something like this. But let's say if your data is something like this, if it falls something like this, if it does not follow basically a straight line, or if it, yeah, if it follows this, then of course your assumption is met. But if it doesn't follow, if it follows something like this in which your, data points are, off track, it's not the straight line, then we'll say that the assumption is not met. Okay, any doubt up till now? Okay, perfect. So now how to address these issues, right? Let's focus on how to address these issues. So let's say, just give me, yeah. Okay, even before that, what I want you to focus on is this particular question. What if the assumptions of linear regressions are not met, right? What if the assumptions of linear regressions are not met? What will happen, right? So what are the consequences is what I'm looking for. And this one interview question can be asked to you also, like what if non-linearity is not met, or what if multicollinearity is not met, right? So let's say linearity. If if let's say if the relationship between the dependent and independent variable is not linear, if the relationship between your dependent and independent variable is not linear, I mean, if the relation itself is not linear, then what it means is linear regression is not an appropriate choice, is not an appropriate choice. So what will you do? What you can do is, maybe in this case, basically using a non-linear regression model, right? A non-linear regression model, or performing some transformation techniques is important to. So if let's say if the relationship is not linear, either use a nonlinear regression model or use some transformation technique to make sure you can use a regression model. It's important to make sure regression model can be used. Okay, so this is the first thing, which is linearity. Second, heteroscedasticity. So as I said before also, if let's say if there is a presence of if there is a presence of heteroscedasticity, then it will impact the standard errors, will impact the standard errors, and if it impacts the standard errors, okay, it will impact the standard errors of the coefficient, right? And because of which the coefficient that we are getting, right, can be biased or inaccurate. So So this is what will happen, right? If let's say if we see the presence of heteroscedasticity, now autocorrelation, right? So if let's say if the errors are autocorrelated, which means that okay, the previous autocorrelation actually impacts the current autocorrelation, then we know that this will violate the assumption and can lead to incorrect model parameters or incorrect model coefficients. So if this will lead to incorrect model coefficients. Also, when we see autocorrelation, the error term will be impacted. And once the error term is impacted, what will happen is the model will produce inaccurate results. So as I told you up, right, in the beginning, that the difference between your actual value and your predicted value will increase and increase. If you see that this difference will increase and increase and increase. Why? Because this error is impacting this error, is impacting this error. So the error will flow throughout your model, right? Then fourth is multicollinearity. See, once you have multicollinearity, or let's say if you have higher correlation between your independent variable, then your coefficients will be inflated. Coefficients will be inflated, making it difficult to identify. So making it difficult to identify which variables are contributing, which variables are contributing to the model. So, I mean, these are, some of the common interview questions which are generally asked in your interviews. And I guess this covers most of it. So maybe in the next session, I'll walk you through some other interview questions. But for this session, this is it. I guess we covered how many? I guess close to 8 or 9 interview questions. I guess 9 interview questions. So yeah, I'm about to stop this recording. And if in case you have any doubt, let's take it further.